This is problem 28.41, and it says that a proton is at rest at the plane boundary of a region containing a uniform electric or uniform magnetic field B. So this is our proton, and sitting right there, no velocity. So that's what we have here. Initial velocity of the proton, 0. We also know a couple more things about the proton. We know that its charge is equal to E, and we know what its mass is, which we're going to call MP, but it's a known value. An alpha particle moving horizontally makes head-on collision with the proton. So this is our alpha particle, and it hits our proton. We know a couple things about the alpha particle too. One, its initial velocity is not 0. We know that its charge is twice that of our electron, but it's also positive. And we know that its mass is 4 times that of the proton. Immediately after the collision, both particles enter the magnetic field. So here, the proton enters, and something happens to it, and the alpha particle enters, and something happens to it. Now we're told that the radius of the proton's trajectory is r, so capital R. We know what that is. The mass of the alpha particle, we are told, 4 times that of the proton, charge is twice that of the proton. Find its radius of the alpha particle. So we want to figure out what the radius is, which we're going to call r sub a, given big R here. So we're going to start off by dealing with a couple of laws that we saw in Phys 204. So the first one is conservation of momentum. We have mv initial. So initially we had the mass of the, this is the alpha particle, right? So mass of the alpha particle is 4 times mp. That's all that is here, times its initial velocity. And then the final momentum is that of the alpha particle, which is just m times v, where m is 4mp, and its final velocity, we're just going to call v alpha, plus the mass of the proton times its final velocity, which we're just going to call vp. So now we have, if we cancel out the mps everywhere, 4vi is equal to 4v alpha plus vp. Again, this is just saying this is the initial velocity of the alpha particle, final velocity of the alpha particle, final velocity of the proton. This is the first equation we're going to use, and we're going to call this equation 1. We're also going to use an equation for the relative velocities. So we know that VA initial, which we've just been calling VI, there's a lot of notation things here. You can really do whatever you want as long as you remember what everything means. So this is the initial velocity of the alpha particle, which we can call VI. Final velocity of the alpha particle is equal to the initial velocity of the proton, and that's 0, plus the final velocity of the proton, which we're just going to call Vp. Rearrange it, and we get Vi. This is the initial velocity of the alpha particle is equal to Vp, velocity of the proton at the end, minus V alpha. We're going to insert this here into equation 1. So by doing this, all we did is here, take this, shove it there, and we get 4Vp minus Va. And on the right-hand side here, we get this 4Va plus Vp. Move things around until they look nicer, and we get Va, the final velocity of the alpha particle, is equal to 3/8 that of the velocity of the proton. So we're going to be using this equation in a bit, right? Because the idea is we don't necessarily care about that directly. We care about what the radius is. And to do that, we go back to the fact that the sum of all the forces is equal to the mass times the acceleration. For the proton specifically, well, we know that this is true regardless. This is the magnetic force, QV cross B, where V, this is just going to be VP, which is right here. And then what we're going to do is say, well, this is equal to Q, magnitude of V, magnitude of B, sine of theta, where theta is the angle between V and B. And in the problem, we are told that they're perpendicular, right? So here we have B going in this direction. So that means theta is 90 degrees. Sine of 90 is 1, so we don't have to worry about that. Now Q, we know what the charge of the proton is. It's E. So all we did here was take this, plug that in here where we have E, Vp, the velocity of the proton, times magnetic field, sine of theta, and that's just 1. And that's how we go from this line to the next line. Now we know that it's equal to mass times the acceleration, but as we've seen, whenever we have something like this, we know there's going to be this curving motion that's happening. So it's going to be the centripetal acceleration like we saw in classical mechanics. So that's going to be m, mass of the proton, times Vp squared, the velocity of the proton squared, divided by its radius of curvature, and we're told that radius of curvature is r. So then we get this. E Vp b is equal to mp Vp squared over r. We're going to cancel out one of these velocities, isolate for the velocity, and we find this. The velocity of the proton is equal to E, its electric charge, times the value of the magnetic field, the magnitude, times its radius of curvature, divided by the mass of the proton. We know all these things, and we're told, well, it's r. We're not trying to figure out what r is. We're just going to assume that r is some number that we're given. This is going to be super useful, and we see that that is directly related to the velocity of the alpha particle, right? So we know this, plug that in there, and we know that too. We're going to do a very similar thing now for the alpha particle. So here, the sum of the forces, again, it's going to be this equation here, where Q, instead of being E, is actually 2E. We know that its velocity is going to be VA, and we know that we have B, sine of 90. We know sine of 90 is equal to 1, so that's fine. And on the right-hand side here, it's the same equation where this is the mass of the alpha particle, which is 4mp VA squared divided by R alpha. All we're doing here is isolating for R alpha because that's what we're really interested in, right? So we're taking this equation, this is equal to 1. We have R alpha is equal to 2 times the mass of the proton times V alpha divided by E. Now remember, we know what V alpha is. It's this. So it's 3.8 Vp. So we take that and we go here, and that's what we got here. V alpha is 3/8 times the velocity of the proton. So here we have this, but we also know what Vp is because we figured out what that is. So we plug that in here. So we plug everything in, and then lots of stuff start canceling out. So we have the proton mass cancels out, the E cancels out, B cancels out, and all we're left with is this. The radius of curvature of the alpha particle is equal to 3/4 that of the proton. And that is the answer to our problem.